Okay, this embayment model, except these two dispersion part, and those are exactly the same that we have seen before. But now we have one more term which is dispersion, but equation itself is a little longer, but it's not too much complicated to solve. And if we assume steady state, we can say it's 0 and 0, and we have two unknowns and two equations. Still, there is no problem that we can solve for C1 and C2. Okay, and in page 144, it had something about salinity equation. And 1 and 2, and somehow if we have salinity, and this one is like, let's say, S1 is here, S2 is there, and then, what does it say? And let's say 0.2, okay. And if you have a salinity, so how much salt in your water? That's the salinity, is concentration of your salt in your water. And if for salinity, we usually say decay is 0, because we assume my salt doesn't have any decay. And if we know some flow rate and the loading rate, and in steady state, if we put this at 0, and we can rearrange this equation to calculate E prime. And sometimes if you know S1 and S2, if you can measure those two, then you can estimate this for the number there. So that's one way to calculate this for the number. In here, conservative means conservative is something that does not change. In Korean, this is very 보수적이다 그런 얘기죠. Right? Conservative does not want to change. It means no decay, no reaction. Alright. And this one is the something. This is one of the samples that we used for other study, and this is about lake, and that has two different layers in a vertical way. One is upper layer, and then this lower layer. And we can say this one is okay, C1 and C2. And also we can count the number of arrows, something coming in, going out. So coming in and going out, and reaction, and then this one is settling, and that's going out. This is going to be like KCV, and with dispersion. So let's talk about one. One is W1 there, the QC1 out there, and the dispersion between 1 and 2. Since I'm the host, I'll be at the last part, okay? And KCV, and this is decay, and VAC, this is settling, okay? And then here, I have settling coming in, going out, and so something release, this one, and then decay. In here, as you can see, we have no Q. So we have no Q, no W, and we have KCV, VAC, and something coming in from there, which is exactly this amount right there, and then something coming in, release from the bottom, and we have dispersion. Since we're talking about number 2, I'm the host, I'm going to be at the last part in my parenthesis. Okay? So, this is easy. Stratified means we have a layer, 2 layers, 2 strata, and then there's a layer. So vertical dispersion coefficient and time time variable solution. Actually, we are almost done for the content that we are in our textbook, but this is somewhere from somewhere else. And there's one of the example that is other Steve Chakma's book, and it's a little bit rough calculation. But now we want to calculate dispersion number between upper layer and lower layer. Upper layer is 1, lower layer is 2. Okay, what is E if we have data? So in here we use the different temperature. Temperature data in 60 days. It's a little rough, but it shows you the general way how to calculate temperature. For E2, and since when we talk about concentration, we use this kind of expression, but you can use this for temperature as well. Okay? And in here we have no Q, no W, right? And also in here we have only maybe dispersion between T1 and T2. And for temperature we have no decay, no settling. So only this thing is what you need. But in here, as we talked about, this one is kind of we can just convert it back to the original form. Okay? So dispersion number and area maybe we can measure. Delta X maybe we can measure. So we can just, this whole thing actually was E prime before. Okay? And in here, let's say they have Z distance between two is now what? Distance between those two. Okay, so they will use this kind of equation, but now they will use this form to calculate my E. So in here, I will just rewrite that, and that is like T2 and time, let's see, they have a T minus 1 and T2 T. This is delta T equals EA delta X and T1 actually average T2 average. So in here we can just rearrange this equation to come up with this kind of relation right here. So actually that equation, this equation is the same, and only thing that I have different in here is Z, and I think since we are talking about delta X, you can use, I think, Z. Actually, that's the distance between those two. So this is the form of equation that you can use for estimation of E12. And as you can see, Z is 700 meter, 700 right there. V is, if you have V, this is V, right? Okay, we can just put it there. If you need A is okay. And then we can now talk about these other terms. Delta T in here is, it says, and I don't have full question, but in this case, they have a from mid-January to December last year. No, just hang on a second. Mid-January, okay, this February. So time interval between measurement is 30 days. Okay? So delta t, in here we'll just put 30 days. Okay. So, and only thing that we need is T1, T2, and this strange looking things here. And then in mid-January, in the, let's say, 15th of January, my T1 and T2 is 3.18 and 3.3. So we're just 3.3, 3.18. Okay? And this is the temperature of number 2 in two different times. So T2 T2 in December was 5.18. T2 in February was 2. So now we have 5.18 and 2. But February, December is just about 60 days. 60 days. Okay? So in here we have 2 times 30. Well, it's maybe a little rough. Not really precise. But just to give you an idea. And actually, if you have just that much rough data, that's the best you can do. Okay? In 2 different times, you have a measurement for temperature for T2, and if you have somehow the someday, and if you have a temperature for upper and lower layer, and I don't fully agree with this method, but we can just can kind of follow the idea, and sometimes this kind of process help us to understand the situation better. So, and I just want to show you the example how to calculate this particular number. Okay, and sometimes many other scholars try to measure this particular number, and he measured this particular number like that. And some others, they have calculated n, and that is something like this, and n is defined as the density difference per depth and gravity acceleration and density. So that's another way. So I just wanted to share the different approaches to do something like that. For n, some n can be this much and some n can be this much. If n is this much, and then EZ can be that much, something like that. So those are the examples. Okay? These are not on your textbook. I just got those from other references. So I just wanted to show you how it looks like. All right, and the 8.4.2 is a steady state concentration, and I want you to take a look at 145 right there, and then try to solve the equation, and then give it to me by Monday next week. It's easy. And time variable solution, in other words, we can actually solve this equation for a steady state which is 0 and 0. And also if those are not 0, and then we practiced before how we can play with that. But in that example, we didn't have this constant term before. So the situation was simple, but in this case, we have, in real situation, we have something coming in and going out, and then the equation can be a little bit more complicated. But in chapter 7, we studied how to solve systems of differential equation. Once you have dCdt for one thing and dCdt for the other, then we can just repeat the same step and per each time step and move along. You can just move delta T away, and then step by step you can calculate the solution. So if you cannot solve the equation by your hand, you can use the computer so that you can have the solution for each time step. So that's another way you can do that. All right. So that's time variable solution, and then 8.5 in 149 and 151 actually, conduction and convection, and they explain the term or the definition of term like that. Conduction is kind of a heat transfer, 전도, right? Convection is kind of movement of air, it's Daejeon. So conduction is moving along the material, inside the material, but convection is kind of, because of density difference, they can move up and down. So there is a free convection, it's kind of natural process. But first convection, if you just have some other storing external force, and then you can make it faster, like the mixing in the jar. And these are just extra. And I have this one. If you have a lake, if you have a solar energy, and then we can have a very warm water at the upper hand side, the upper layer, and cold water in the lower layer, because this density is lighter. This is and this is greater, and we have kind of it's like we have a film between those two layers, and dispersion is going to be very much small, because this is mixed together very well, because this is homogeneous. So browning movement can occur here and there, but when they have a deep density difference like this, it's like warm water and cold water. You can actually, when you go to swimming pool or the public bath, you can, or if you have a little bowl in your yard, 대야 같은데, and then if you take your finger and you can feel the hot warm water in the upper layer and less warm water in the lower layer, and they're going to be like that. They're going to be like behave like water and oil. 기름과 물처럼 서로 안 섞여요. So there are different. The dispersion is going to become very small. So it's like actually like different layers. This is in this case we call this lake stratified. 성층화된, right? But if we have too much sunlight and enough nutrient, we can have algal bloom. So your water will become very green if it rains, and if you have a lot of dirty water, right? And then they can move. Dirty water that has relatively low temperature than your upper layer, and then they will have a lot of dirty material inside. So their density is going to be a little bit higher than this one. So when they meet the lake, and then they can going to move downward because this is heavier. But if they meet really heavy water that has a more even greater density than this, then they cannot go lower. Then they will move along the somewhere in an equilibrium way. This is about energy difference, okay? And then we call that as density current. It happens in your lake, especially in rainy season and flood season for us, and they can stay there for several months, and they can decompose inside because they have a lot of stuff. what is this, maybe plant, animal, and dead bodies, and they can mix together, but they can go through decomposition with very less oxygen. So they can become very dark, black water. And so they sometimes discharge black water at the end of summer. It has a lot of problem. Because it contains a lot of organic material. If you use this water for your water supply, you will eventually have a lot of THN concentration, because THN is about organic material and chloride, your disinfectant. So this is the problem. Anyway, so when you discharge, you have dark water, and that's a problem. Well, we know the definition of density, definition of weight, and definition of specific weight, so I don't want to repeat that, but I just have it. Why density of water is different? I think this one, I can cover this in what called management class, so I just want you to read it over. And because, and we know, because water molecule is, Ag2 is one molecule, but they have a kind of a bond, hydrogen bond, and then they somehow have a distance between molecules, and they say they somehow vibrate all the time. But if you have low temperature, and the vibration energy is going to be less and less, and their distance is going to be closer and closer to it. So they will just get together. That's why as you have lower temperature, they will kind of get together, so their density is going to be going high. But we know ice has temperature 0, but ice can float over water. That means ice is lighter than water. That is a little bit confusing, because I said as temperature is going down, water molecule is getting closer to each other, and then density is going to be higher. The reason why ice is lighter than water in this temperature was between 4 and 0, water, liquid, is transforming to solid, which is ice. In that case, the layer, or this, the layout of your molecule is going to be very uniform. So, because of different arrangement of molecule, we have different density. 물 분자 연결한 수소 결합이 점점 진동이 작아지면서 모이긴 하는데 4도씨까지 모이고 4도씨부터 0도씨까지는 이게 액체에서 고체로 바뀌면서, 액체는 랜덤하게 분자가 섞여 있지만 고체는 아주 질서정연하게 되어 있기 때문에 사이사이가 뜨게 되어 있어요. 그래서 질서정연하게 자리를 잡으면서 다시 덴시티가 줄어드는 거죠. 0도씨가 돼서 고체가 된 상태에서는 다시 또 온도가 내려갈수록 다시 덴시티가 늘어납니다. 점점 줄어드니까. 그렇기 때문에 물과 아이스가 다르다는 것에, 이건 appendix니까 성층현상은 이 한국말로 설명하겠습니다. 한국말로 됐으니까 물은 비열이라고 하는 것은 물을 데우는데 필요한 에너지입니다. 에너지가 상대적으로 높다고 표현합니다. 1.0이 높은 편이래요. 그래서 그 무슨 소리냐면 외부에서 오는 에너지를 잘 흡수한다, 잘 가지고 있다는 뜻입니다. 그러니까 잘 데워진다는 얘기겠죠. 잘 데워지, 위층은 잘 데워지지만 자기가 다 가져가 버려요. 아래층으로 전달 안 하는 거예요. 얌체처럼 위층만 데워져요. 위층만 따뜻해지고 아래층은 안 따뜻해지니까 위층은 물도가 낮고 아래층은 물도가 높은 상태로 그대로 남아있는 거기 때문에, 그렇게 되면 서로 물성이 달라지는 거죠. 밀도가 달라지고 물성이 달라져 서로 기름과 물처럼 논다. 그래서 결국은 그때 확산은 잘 안 일어난다. 그래서 그런 것들이 층이 완전히 여름철에 많이 일어나는 게 성층 현상이다. 는 것이고 우리가 실제로 이 호수나 이 하천이나 이런 걸 모델링할 때 그런 이 수직 방향의 디스퍼전 코에피션트에 대한 고민을 할 수밖에 없습니다. 왜냐하면 녹주현상 같은 거에 굉장히 중요한 현상이기 때문에 그렇습니다. 그래서 thermal certification은 그렇게 설명했습니다. 그래서 예를 들어서 예를 들어 4도씨, 5도씨 사이에는 density difference가 얼마나 있겠죠. 근데 24도와 25도는 또 얼마나 있을 것이고 29도, 30도 얼마나 있을 것입니다. 근데 4도씨, 5도씨 여러분들은 density difference가 크지 않은데 온도가 높을수록 아마 density difference가 더 커지는 거죠. 그래가지고 나중에 따뜻해지면 믹스가 안 됩니다. 그래서 만약에 이것을 성층 현상을 우리가 안 일으켜, 그러니까 좀 없으면 좋겠다라는 차원에서 우리가 믹서를 쓰죠. 많이 씁니다. 에어레이터라도 쓰는데 그것이 온도가 낮을 때부터 이게 이 믹서를 해야 돌지 다 데워지고 난 다음에는 믹싱해봤자 도로 다시 원위치 되기 때문에 아무리 파워를 많이 써도 효율이 안 나죠. 그래서 봄철부터 수공해서 그런 걸 인공 기조라고 해서 많이 쓰는데 소용이 없다. 일단 생기고 나면 소용이 없다. 그런 얘기입니다. 생기기 전에부터 돌리기 시작해서 계속 돌리게 해줘야 되는데 엄청난 에너지 낭비죠. 그리고 이제 서로 디스퍼전이 안 일어나기 때문에 위하고 아래 물질 자자에 앉아서 서로 chemically different한 물이 생기는 거고 그래서 굉장히 나름대로 에러상이 많죠. 아까 보게 되면 아래쪽에서는 그 VR 릴리즈가 있었어요. 포스포러스나 나이트로젠 같은 경우에는 바닥에서 농축이 됩니다. 그게 상층으로 전달되는데 바닥이 아직 또 진국이 되겠죠? 진국이 됩니다. 그런 문제가 또 있고 나중에 가을철에 섞이게 되면은 아주 수질이 아주 나빠지는 그런 일이 생기게 됩니다. 그래서 지금 대충 보게 되면 온도차 가지고 상층, 하층, 중간에 이렇게 안만 해도 전이층, 변하는 층이 있겠죠? 그걸 이제 베타, 위는 에피, 밑에 하이포 이렇게 해서 변하고 주로 이제 상층과 하층으로 이걸 무시해서 하는 경우가 있는데 중간층이 그래도 꽤나 두꺼우니까 반드시 변하는 층이 있겠죠. 뭐 어떻게든 하게 되면 이것이 아래쪽이 굉장히 낮은 물과 굉장히 높은 물. 대청호 같은 경우는 40도쯤 되는데 여름에도 바닥은 6도밖에 안 돼요. 위에가 한 30도 정도 돼도 바닥은 6도 정도밖에 안 됩니다. 그렇기 때문에 뭐 엄청난 차이가 나는 거죠. 예, 그래서 제가 시험한 걸 많이 보여드렸고요. 턴오버는 가을에서 다 뒤집어진다는 그런 현상이고요. 그것은 지금 몇 때까지는 제가 수온의 그 밀도 가지고 얘기를 했는데 생물을 하시는 분들은 광량으로 구별합니다. 그러니까 빛이 충분히 통과하는 데까지가 광량, 진광대, 유포틱. U는 많다, 포틱은 광이라는 뜻이죠. 광이 많은 지역이고 프로펀달은 바닥이라는 지역인데 그 밑에는 어둡다라는 뜻입니다. 쉽게 얘기해서 밝은 지역과 어두운 지역 나눠서 밝은 지역은 광합성이 있겠죠. 그래서 구분하는 방법이 나는 그 수온으로도 우리 보통 많이 하는데 생물 하시는 분들은 광합성 하는 지역에서 빛에 투과되는 깊이까지를 해서 그걸 이제 바이올로지컬 자원이라고 부르는 겁니다. 그래서 인포틱 내지는 프로펀달 이렇게 얘기하고 리토럴, 리토 같은 경우에 흙이라는 뜻이에요. 벤트는 이제 바닥이라는 뜻이고 그래서 그렇게 해서 그런 것도 있으니까 서로 비슷할 수도 있겠지만 반드시 비슷한 건 아니죠. 데피니션 자체가 다르고요. 그러니까 참고하셔라. 진광대에서 가장 많이 생물이 자란다 그런 영향들. 그렇습니다. Okay, then this is your item to play with, and please enjoy it. Okay. So we are done with chapter 8. Next week we are going to be done with chapter 9, and pretty soon we are going to be done with this whole book. Congratulations. And chapter 9 is about distributed system. And so we are going to talk about a little more equations. And chapter 9 is kind of highlight. And then I will talk about a little bit about the chapter 10. And then we are almost done because in your 40K